So let's now try to derive the order conditions for a three-stage third-order accurate explicit Runge-Kutta method. For an explicit three-stage third-order RK method. And before we do this, it's like let's just try to simplify a bit, or if you will, it's like impose constraints on the relationships between the A's, it's like the B's and the C's. All right. So let's just consider the following. So let's consider a case where say Tn is 0, and then y of t is just t. All right, so that corresponds to a differential equation, obviously, which has that y at 0 is equal to 0, and then y prime is equal to just some constant, say 1. Okay, so that's a simple case. It's like, and of course, if you can't exactly integrate a differential equation like that, it's like then there's a real problem. So this is an example of the kind of differential equation you need to be able to solve. It's like in order for the method to be first order accurate. So the basic observation, if you will, is that for first order accuracy, right, you need to be able to need to sort of obtain the exact solution of a solution which looks like y of t is equal to t. Okay. All right. So let's look at my numerical method. Right. So the numerical method says the following: that you want y I to be just the sum from yn plus h times the sum from j is equal to 1 to s of aij, right, f evaluated at yj, and then tn plus cjh. Okay. So, and then yn plus 1 is equal to yn plus h times the sum from j, well, let's write this as I equals 1 to s of bi f evaluated at yi tn plus cih. Okay, so let's just see what has to happen. Okay, so let's write down what yi is. Okay, in the case where you have a differential equation where the derivative is just a constant. So yi is equal to yn plus h times the sum of j equals 1 to s of aij, and then f evaluated at any of the yj's is just 1, right? So that's just 1, okay? And then we want to write down what yn plus 1 is. So yn plus 1 is equal to yn plus h sum of I equals 1 to s of bi, and then f evaluated at this point again, and that's again identically 1. Right, so that tells you several things. So again, the yi's, if you will, it's like can be viewed as approximations of y at tn plus cih. Okay, and so in this case, that means that we want this thing to equal to and yn is 0. Okay, so you want this to basically be equal to yn plus h times ci. Okay, and then you want this thing to be equal to yn plus h. Okay, So that gives you certain constraints. It's like on the aij's and the bi's. So this condition here tells you that the sum of the aij's, right, over j from 1 to s should equal to ci. So more or less what that means is that when you sum up the rows, it's like of this A matrix, they should correspond to the corresponding value of C. Okay? And then the second condition, it's like what you want is that the sum of I equals 1 to S of BI is equal to 1. And you can view this as morally being in the same sense as this equation. The BI's, of course, are the quadrature weights associated with the final time step corresponding to essentially like a CI equals 1. So these two are morally, it's like the same type of condition, if you will. Okay, and it's just that in this last case, it's like the CI in some sense is 1 here. Okay. So these conditions are necessary, as you might expect, in order for the internal stage values, it's like to be an accurate approximation of this simple exact solution of a differential equation corresponding to a constant vector field. Okay. All right. So that's just one observation, which is going to turn out to be useful. So then the sum over j equals 1 to s of aij is equal to ci. That's one condition you need for the method to be first order accurate. And then the sum from I equals 1 to s of bi has to be equal to 1. Okay? All right, so this is necessary for first order accuracy. Okay. All right, and if you recall, it's like when we're deriving this explicit two-stage second-order accurate method, we did this thing, it's like where we assumed, or at least we considered the case, it's like where the vector field is non-autonomous. It depends on both position and time. And as we saw, it's like that sort of required you to consider a lot of terms. So it turns out that at least when you're just looking at third-order accuracy, it's not necessary for you to consider the full non-autonomous case, and it's possible to just do the analysis just in the autonomous case. So this is a remark, right, that for sort of second order, well actually up to, let me rephrase that, for up to third order accuracy, up to the sort of third order order conditions, it suffices to study the case of sort of autonomous differential equations. Which is to say that y prime is only a function of y, and it doesn't depend sort of explicitly on time. Okay, so I'm not going to justify this here. It's like it does simplify the analysis quite a bit. It's like when you're trying to derive these order conditions for the third order case, but it doesn't hold true if you're trying to push the analysis up to higher than third order. Okay, so I'll just sort of state this without proof, and then we'll try to do the error analysis. It's like for this explicit three-stage third order Runge-Kutta method. Okay, so you have C1, C2, and C3. You have A21, A31, A32, right? And then you have B1, B2, and B3. Okay, and so by using this condition, it's like you can simplify things quite a bit, because what you can do is that you can get rid of this, right? This is just C2, and you can rewrite this as C3 minus A 3, 2. Okay, so that's basically what's going to happen in the analysis, and we'll see where that goes. Okay, so you have y1 is equal to yn. Okay, so this implies that f evaluated at y1. So recall I'm just looking at vector fields which are autonomous, so there's no time dependence now, so I've dropped the time dependence. So f at y1 is equal to f at yn, which I'm just going to denote by f, right? So if it's expanded about yn, it's like then I'm just going to drop the y dependence here. Okay, so y2 then is yn plus h times c2 f, right? So so this means that if I look at f at y2, okay, this is f at y plus h c2f. So yeah, I guess it's like, again, it's like I'm, well, let me just write this as yn then. Okay, and what happens then is that you can write this expanded about the point yn. So this is just f, it's like to leading order. Then there's a h times c2f, and then there's a df dy term. Okay, and then you can look at the next higher order term, right, which is now the second derivative, it's like of f. Okay, so and then it's like hc2f squared, right? There's a hc2f squared over 2, and then it's like f yy, if you will. Okay, all right, and then plus something which is big O of h cubed. And then let me write y3 over here because it's a little bit more involved. So y3 is equal to y plus h c3 minus a32 times f at y1, right, plus h a32 f at y2. Okay, so that's equal to, well, let me just put yn here, sorry. Okay, so yn plus h c3 minus a32 f at y1, right, is just f. Okay, plus h a32 f at y2, so I have this expansion here. Okay, so that's h c2 f fy plus h squared c2 squared over 2 f yy f squared, right, plus big O of h cubed. Okay, so let's see what this looks like. So this is yn plus h. So there's a h c3 times f term, and there's a minus h a32 times f term, but the okay, so let's see. I'm sorry, I'm missing a term here. There was the leading f term here, right? So there's a f plus this. Okay, so there's a hc3 f term, there's a minus h a32 times f term, but that cancels out with the h a32 times f term here. So this term cancels out with this term. So the h term just involves hc3f, all right? And then then the next higher order terms are the h squared terms. There's a h squared A32 C2 FYF term, so that comes in this piece. And then this term here is cubic, right? Plus a cubic term, which is H cubed A32 C2 squared over 2. And then FYY F squared plus order H to the 4th. Okay. All right, so I don't actually need it to that power because what's going to happen is that all I really care about is y at n plus 1, okay? But, you know, it's like, so nevertheless, it's like that's reasonable. Okay, so so you can look at what f at y3 looks like. Okay, so it's actually sufficient to just sort of drop the this cubic in h term in the analysis. So anyway, f at y3 is f at yn plus h c3f plus h squared a32 c2 fyf plus something which is order h cubed. All right, so I've dropped this h cubed term. And then I can do, again, a Taylor expansion in this. So f, right, plus a fy h term. So h is this actually whole thing here, right? Okay. So there's a hc3f plus h squared a32 c2 fyf term. Right, and I'm only really interested in things up to order h cubed, so plus order h cubed. Okay, and then there's a fyy, right? And then again there's a h cubed f plus h squared a32 c2 fyf plus order h cubed. And then this thing is squared, and then it's a factor of 1/2, right? And sorry, what h3? That's what I mean by this. Okay. Sorry, I mean hc3, right? Okay, and then it's like you can check that the shift, it's like it's at least of order h. So the term which I'm missing, if I take it up to quadratic, is order h cubed as well. So I'm just trying to be consistent here. All right, so let me try to simplify that a little bit more and then rewrite some of the things we already have. Okay, so at the end of the day, all I really need to know is what the series expansion for f at the internal stages are. So I have f at y1 is just f, right? F at y2 is equal to f plus h c2 f fy plus basically h c2 f squared over 2 fyy plus order h cubed. And then let me try to simplify this. So f at y3 is equal to f plus okay, so I only care about the expansion up to things which are big O of, I only want the expansion, it's like with an error, it's like up to big O of h cubed. Okay, so I have a hc3 f fy plus h squared a32 c2 fy squared f, right, plus 1/2 fyy h squared c3f. Okay, So if I omit the error terms, it's like I just take the square of this, right? Then the other term you have is a h cubed term. So I'm not going to include that. So that's a h c3 squared f squared term plus big O of h cubed. Okay, let me just check that's right. Okay, so that's a 1/2. Yeah, all right. So let me just try to simplify that a little bit more. So that's f plus h c3 f fy plus h squared, right? A 32 c2 fy squared fy plus 1/2 c3 squared f squared fyy plus big O of h cubed. Okay? All right. So now we're almost at the finish line. Okay. So then yn plus 1 is equal to yn plus hb1 f plus hb2, right? And then that's f at y2, so I'm going to replace it with this thing, b2 f plus hc2 f fy, right, plus okay, so 1/2 h squared c2 squared f squared fyy. Okay, plus hb3 f plus hc3 f fy plus h squared a 32 c2 fy squared f plus 1/2 c3 squared fyy plus big O of basically h to the 4 now, right? And that's because each of these terms are being multiplied by a factor of h. So when you've taken the series expansion for the vector fields at the internal stages to order h cubed, when you use that in the final equation for yn plus 1, the error you have is order h to the 4. Okay, and that's of course what you need, because you want to have that the truncation error is big O of h to the p plus 1, and then we're looking for a third order accurate method here where p is equal to 3, so you need to take expansions where the omitted terms are big O of h to the p plus 1, which is big O of h to the p plus h to the 4th. Okay. So now, as it turns out, it's like you'll see that there are f's, it's like floating around at a bunch of places. Okay, so let's just try to collect them. So you get yn plus h, b1 plus b2 plus b3 f, right? So these, all these terms have a hf term. It's like with some coefficient. Okay, and then let's look at the h squared term. So h squared. Okay, h squared is a c2b2 term, right? c2b2, right, plus c3b3 multiplied into fyf. Okay, so there's one term coming from here, and there's one term coming from here. All right. Okay, and then there's a h cubed term. So the h cubed term comes from this term here, as well as these terms here. Okay. All right. So it looks like h cubed 1/2 b2 c2 squared plus b3 c3 squared fyy f squared. Right. There's an fyy f squared term here. There's a fyy f squared term here, and then there's also a fy squared f term. Okay. So plus b3a32 c2 fy squared f term plus something which is now big O of h to the 4. Okay, so then you have to compare this. It's like with the Taylor expansion, okay, and that's a little bit easier now. So so you know y prime is equal to f, right? You don't have the time derivative piece because we've assumed that you don't have the partial respective time because we've assumed that the vector field is autonomous, okay? But you still have this, you know, it's like f d dy term as the proxy for the total derivative, okay? So this gives you a f fy when you're doing the second derivative, and then you want to take it at least the third derivative because you want the truncation error to be big O of h to the 4th. So y triple prime is f d dy of f fy, right? So you have to apply the product rule to that. Okay, so if I differentiate the f first, I get a f fy term, right? Plus, if I leave the f, I get f squared fyy. Right, so that's consistent with what you see, right? There's a fyy f squared term, fyy f squared term, and then there's a fy squared f term, fy squared f term. Okay, so everything is consistent. All right, so this is just the, you know, it's like the iterated derivatives. It's like the solution. Then the Taylor method says that y at tn plus h, right, is equal to yn plus h times f, right, plus h squared over 2 f fy plus h cubed over 6 f fy squared plus f squared fyy plus big O of h to the 4. Okay, so now it's like you are in a position, it's like to again equate coefficients. It's like between the Taylor expansion of the Runge-Kutta method and then the Taylor method. Okay, so so when the dust settles, what you get is the following: that you have this hf term corresponds to this. So that says that b1 plus b2 plus b3 is equal to 1. Right, so you look at now for the h squared fyf term, which is here. Okay, so this is telling you that this coefficient is equal to 1/2. Okay, so that's saying that let's write it as b2 c2 plus b3 c3 is equal to 1/2. And if you will, I can write down where this comes from. This is the hf term. This is the h squared fy term. Okay, and then there's sort of two other terms, right? There's the h cubed fyy f squared term, and there's the h cubed fy squared f term. So let's look at the h cubed fyy f squared term. Okay, so that's 1/2 b2 c2 squared plus b3 c3 squared is equal to 1/6. Right, or you can just multiply it by 2. It's like you get b2 c2 squared plus b3 c3. Wait. Sorry, that's a squared, right? Okay, c3 squared is equal to 1/3, right? And then there's finally the h cubed fy squared f term. Okay, and then that is just b3a32 c2, okay, is equal to 1/6. Okay, so those give you the order conditions for a third order 3-stage explicit Runge-Kutta method with the simplifying assumption that we're just looking at the case of an autonomous differential equation. And as a reminder, that doesn't always work. In particular, it doesn't work for doing the analysis beyond the third order, but for the third order, it's like that does work. And then let me sort of just give you some examples of Runge-Kutta methods which satisfy these third order conditions. So these are just some examples of RK methods, explicit RK three-stage third order Runge-Kutta methods. So there's one which is has 0, 1 half, and 1 as the stage numbers, right? Okay, there's -1 and 2, so 1, 6, 2/3, and 1, 6. Okay, that's one possibility. It's like you can check. It's like satisfies. It's like these order conditions. There's what is known as the Nystrom scheme. Okay, which looks like 0, 2/3, 2/3. There's a 2/3 here. 0, 2/3, and then 1/4, 3/8, and 3/8. So it turns out that you can also, it's like push this forward, to higher order. It's like the third order. So perhaps the most commonly known fourth order, fourth stage explicit Runge-Kutta method is the following. So this is an example of a fourth stage, fourth order explicit Runge-Kutta method. Okay, and this is sort of very commonly used, not necessarily the best method, but very commonly used. Okay, and then these are the final weights which allow you to combine. It's like the vector fields at the different points to get a approximation of the solution at a new time. Okay. All right. So as you might imagine, it's like if you were to try to use just this kind of Taylor expansion, it's like by brute force, it's like to do this analysis, it becomes really hard. You'll see that even in the case where you're just assuming, where you've made the assumption that the vector field is autonomous, it's like gets a little bit hairy. If you further imagine that you are required to do the analysis for a non-autonomous system to high order, then it becomes much hairier still. So what we'll see, it's like later on, is that there's a very nice sort of combinatorial way of ordering, if you will. It's like the terms, it's like in the Taylor expansion. And that will give you a nice systematic way of doing error analysis. It's like in terms of what are called rooted trees. And this is sort of an approach which was pioneered, it's like by John Butcher at the University of Auckland. So I'll talk about that later.